Welcome to our next lesson on the balances forces model unit. Here we are focusing on learning goal number 2 in the balanced forces model unit, and specifically success criterion letter C. So looking at that learning goal and success criterion, our learning goal is I understand how to quantify force. And this particular success criterion we were looking at, I can draw quantitative force diagrams. Now let's just take a moment to review our last two success criteria, reviewing mass versus weight, because that will be important for drawing these quantitative force diagrams. Recall that mass is the amount of matter in an object, and this would be measured in grams, kilograms, milligrams, micrograms, anything with the unit grams in it. The most common unit that we see, as we know, is kilograms. So this is what we typically see in our questions and problems, but other grams units would also be mass. Weight, we know, is the force of gravity acting on an object, and that is measured in newtons. At least in science, that's what we like to use, the metric system. Another unit that we're all familiar with would be the unit pound, because pound and newtons are both units of force. And then recall that these two things are related, mass and weight. They are related by the gravitational field strength at a particular location. So for example, Earth's gravitational field strength is 10 newtons per kilogram, whereas the moon's gravitational field strength is 1.63 newtons per kilogram, roughly 1/6 of Earth's gravitational field strength. So in other words, whatever your weight is on Earth, you would weigh 1/6 of that approximately on the moon. And so we can use these gravitational field strengths to convert between mass and weight. In fact, this next slide here, I go through just a couple of other quick examples of that. So for example, the question might be, what is the weight on Earth of a 15 kilogram object? So notice we're given the mass of the object. I know it's mass because it's measured in kilograms. And I want to know the object's weight on Earth. So because I'm looking for weight, I'm looking for newtons. So I write question mark newtons equals 15 kilograms. And as we've seen from previous lessons, I know I'm now going to multiply by a fraction. Well, that fraction, my units have to cancel to give me the units I want. So notice kilograms is in the numerator here. It's in the denominator here, so kilograms will cancel. And notice I put newtons on top, so that way I'm left with my unit newtons. And then as far as figuring out what numbers to put where, if we just remember on Earth, there are 10 newtons per every kilogram, so the 10 goes with the newtons, the 1 goes with the kilogram, and I can see here I can just take 15 kilograms times 10, and that will give me my 150, and my unit, as we said, is newtons, because that's what I'm left with. So the weight of this object on Earth would be 150 newtons. Looking at a different sort of question here, now we're asked to find mass. What is the mass of an object that weighs 50 newtons on Earth? So now, because we're looking for mass, we're looking for kilograms. I suppose since this question doesn't say specifically what is the mass in kilograms, we could find our answer in grams or milligrams or something, some other unit. But kilograms is the most convenient because I have this relationship here of 10 newtons per every kilogram. So now I'm going to multiply by a fraction, but this time, notice my newtons has to be in the denominator to cancel with my newtons that I'm starting with. And I want to get kilograms, so that's going to go in the numerator. So recognize that the 10 that did go in the numerator before is now in the denominator. Because recall that it always goes with newtons. It doesn't always go in the numerator, but it does always go with newtons. So newtons will cancel, leaving us with kilograms. And then remember, if it's in the denominator, we divide. So 50 newtons divided by 10, that's going to give me 5. And my unit, again, is kilograms because I'm left with kilograms there. So that's just a quick review of what we've learned about mass versus weight. So let's put this into action and go about drawing a quantitative force diagram. So here's the scenario. We're told to draw a quantitative force diagram for a 4 kilogram book that sits stationary on a level table. So we're going to draw a force diagram, and we'll start by drawing our axes just like we would for any other force diagram, and label them with your x and your y axis. One thing that we will do here that we typically don't do if our force diagram is qualitative, and recall qualitative means without numbers, but now that we will have numbers because it's quantitative, we will define our positive directions. Now it makes no difference which way you choose is positive. You can have this opposite of what I show here, but I'm going to say going to the right is positive on the x-axis, which means going to the left will be negative on the x-axis. And then for the y-axis, I'll say going up is positive, and we'll say down is negative. Again, that could be opposite if you want it to be. You get to decide that as long as you're consistent with your sign conventions, meaning which way is positive, which way is negative, you'll solve these problems just fine. All right, so as far as drawing the force diagram, just start by asking yourself what we always do: what forces are acting on the book? Well, I know there's going to be weight or gravity pulling the book down, so Fg, and notice I have my vector here pointed down. Now one of the things you'll notice is once we get to quantitative force diagrams, meaning we will put numbers with them here in just a bit, unless we are asked specifically to, or unless I ask you specifically to, we typically will not worry about the whole victim agent notation, meaning Fg on book by Earth. Not that it's not important, but once we start putting numbers on this stuff, the force diagrams can get really messy because there's a whole bunch of stuff on there. And so in order to clean it up a little bit, we will typically leave out that victim agent notation. Now the fact that the book is simply just sitting there tells me it's not accelerating, so that means the forces have to be balanced. So I have to have some force pushing up on the book to balance out that force of gravity. Well, since it's sitting on the level table, that would be the normal force from the table. So it would be, if we were to use victim agent notation, it would be Fn on book by table. Now notice those vectors are the same length, and so to indicate that, I need some equality marks that I'll put on there. Now in the past, this would have been all we would have done. If our force diagram was not quantitative, we'd be done, other than we would probably add that victim agent notation. But now we do need numbers. We want a quantitative force diagram, meaning I need to put how much force of gravity, how much normal force is acting in the book. Well, this goes back to the mass. We're told that the mass of the book is 4 kilograms. Again, I know it's a mass because the unit is kilograms, so I need to know what that translates to for a weight. I need to know the weight of the book. So I want to know how many newtons are equal to 4 kilograms. Well, that's the same sort of conversion that we just saw in the last slide. I will multiply by that Earth's gravitational field strength of 10 newtons for every 1 kilogram. Notice kilograms cancel, and I'm left with newtons, and that gives me 40 newtons, because 4 times 10 is 40. So that tells me that the weight of the book, or in other words, the force of gravity, because remember, that's what weight is, it is the force of gravity, is equal to 40 newtons. So I'll just write equals 40 newtons here. Now the fact that I know the normal force has to be the same, I can see that very clearly because of my equality marks. I also know that is 40 newtons. Now one thing to recognize here is, even though we have said up is positive and down is negative, oftentimes the convention is not to put the negative sign in here. I know that this is in the negative direction because it's pointed down, and I've called down on the y-axis negative. It would not be wrong if you wanted to label this specifically negative 40 newtons, if you wanted to do that. But that's the end of our force diagram. We have drawn a quantitative force diagram for a 4 kilogram book sitting stationary on a level table. Let's take a look at one more example here. So this time, you push a shopping cart to the right at a constant velocity. And recall what that means is all of the forces acting on the cart would be balanced. The weight of the cart is 250 newtons. You push with a force of 100 newtons. Draw a quantitative force diagram for the cart. If you need to pause the video and write that stuff out, go ahead and do that. And once you've written out the question, go ahead and play the video and take a look at the example. All right, so we're asked to draw a force diagram. Yes, quantitative, but a force diagram nonetheless. So I need to start by drawing on my axes like we always do, and labeling them X and Y, and then we want to define our positive directions. Because the cart here is moving to the right, notice it says we push a shopping cart to the right at constant velocity. I'm going to say right is positive. Again, you would not have to. You could call left positive if you wanted to. But if right is positive, then left has to be negative. And I'm going to say up is positive, and that makes down negative. Now in this case, we're already given some values for forces. We're told the weight of the cart is 250 newtons. Well, recall weight is the force of gravity. So there's going to be 250 newtons of gravity pulling down on the cart. So I'm just going to go ahead and label that Fg equals 250 newtons. We're also told that we push with a force of 100 newtons. Well, we're told that we are pushing the shopping cart to the right. So I'm going to have a push force, which I will label Fp, notice that here, equals 100 newtons, and it's going right. The other thing to recognize is this. Even though I haven't gotten out a ruler or made sure this is absolutely perfectly to scale, do notice that 250 newtons is over twice as much force as 100 newtons. So that vector needs to be over twice as long. In fact, it should be 2.5 times longer than 100 newtons. Looks like I'm not perfectly to scale here. I just kind of eyeballed it. Looks like my push force should probably be just a bit shorter, but this will work for our purposes here. The point is, whenever you have forces of different sizes, you do want to try to draw your force diagrams to match them as best as you can. Again, they don't need to be perfect, but make them believable. Okay, the fact that the cart is moving at constant velocity tells us that we have to have balanced forces. So I have to have a force to balance out my weight or my gravity. I also have to have a force to balance my push force. Well, on the vertical axis, up and down, I know that force will be the normal force from the floor or whatever I'm pushing the shopping cart on. And because it has to be balanced, I know that also has to equal 250 newtons, same as gravity. And because they're the same size, I need some equality marks, so I'll put some hash marks there. Same thing horizontally. I need a force to balance out the push force. Well, think about what that force would be. If I'm pushing a shopping cart along, say at the grocery store, and it's going at constant velocity, it has to be balanced. The force going the opposite direction would be friction. There's going to be friction acting on the cart. So Ff equal to 100 newtons. And again, it has to be 100 newtons because it has to balance with my push force. And again, because we have the same size of force, I need some equality marks. I've already used a hash mark here, so I'm going to use a different shape. Looks like I chose to use a circle here. You could use a different shape if you wanted, but I will put a circle on those two force vectors to show that they are the same size. And that quantitative force diagram is done. All right, so in this particular lesson, we have looked at learning goal 2, success criterion C. We are working on understanding how to quantify force. And in this particular lesson, we looked at how we draw quantitative force diagrams.